Ah. Okay, so this is our topic for today, and the topic of coherence, and at very short wavelengths, but basically the idea is the same at all wavelengths. And let's see. So yeah, so we're going to, for instance, on the left, what's shown here is a point charge, an electron. It's oscillating in and out of the board, and it's radiating spherical wavefronts, okay? And so if that's the case, if you were to somehow or other know or measure the, let's say, the electric field at some point, any point in here, because you know the wavelength and it's radiating all these nice spherical wavefronts, you would know the phase everywhere. And so we call that spatial, that would be radiation that's spatially coherent. And a property of a point source is it's spatially coherent everywhere. How far you can propagate out, can you go, a meter out and still relate it back to here? That depends on the bandwidth. How many waves of coherence radially out does it have? And that depends on how narrow is the spectrum. But for instance, the spectrum could be limited because the source of oscillation, if it was only 100 cycles, then you can only have 100 cycles of coherence because there's only going to be 100 cycles of the waves. It doesn't exist before that, and it ends after 100 cycles. So a point source that radiates from minus infinity to plus infinity is a purely coherent light source. And if you, one of the key features would be that you can form interference patterns with this radiation. If you were to take it and break it into two parts and bring them back to where they overlap, they would form an interference pattern, so-called fringe pattern. Come back to it again in a moment. But this is the most coherent source you can imagine. Point source oscillating from minus infinity to plus infinity, monochromatically. What's shown on the right here is something where you have a finite wavelength spectrum, not infinitely narrow, and you're only observing it over a finite angle. And because you're only looking at a finite angle, you get diffraction from the edges here, and it affects your ability to see the point source. If you don't get a full view of it, you don't know that it's a point source. It could have been a little bit bigger. So finite source size, finite divergence, and finite duration will affect coherence. So I'll come back to these points later, but just a kind of introduction. A big thing, let me just see, did I make the extra slide? No, I didn't do it. Oh. Here's something you just have to make a note about. So what are some of the properties of coherent radiation? So here are two. One is that you can form interference patterns. With incoherent radiation, you won't get interference patterns. You won't get any of these fringes. If there's a little fringe on the periphery of what you thought was incoherent radiation, well, those little fringes on the edges are telling you, well, it wasn't totally incoherent. It was mostly incoherent. But anyway, coherence, among other things, is the ability to form interference patterns. Another thing is that if it's coherent radiation, you can arrange for it to go out with the minimal amount of divergence. In fact, the size of your source and the wavelength will set some limits, but at any rate, you can have radiation which propagates out. So for instance, a laser pointer is spatially coherent, and it goes out with in a very narrow radiation cone as compared to a light bulb that's just going into 2 pi, 4 pi, okay? So for instance, if you look at this diagram here, forget the blue parts and forget the blue dot for a moment in this stuff. Just look at the purple dot and, okay. This again, what I'm imagining here, it's shown a little bit large, but this purple thing is a point source, and it's radiating spherical waves, which are going all over the place, but I've only shown them for a limited part. They exist further, but that's all I've shown. And this is their wavelength. And at some half angle, there's an aperture here with openings at plus or minus this angle theta. There are little openings that allow the radiation to come through. So as we said, if it's a point source, this is going to be spatially coherent. And for instance, if you knew the phase here, you would know it over here and over here. You could predict it very accurately. Okay, so you put two openings here, apertures or pinholes, and again, the radiation will diffract out of that in both cases. And again, forget the blue dashes for the moment. This radiation, when it reaches this so-called screen, maybe it's X-rays and it's hitting a fluorescent screen and it's producing a light pattern. But at any rate, it's going to produce an interference pattern that's shown here. And what's happening is the path length from this top opening to just on the middle of the screen here, this path length and this path length are exactly the same, so that the electric fields coming through both places are adding up at this point. And what's shown is an amplitude that's high. It's the electric fields have added. If you go a little bit off axis, this path length has become a little bit less. This path length has become a little bit more. And since these are coherent, if that difference in path lengths is just enough to put them out of phase with each other, so the electric fields are opposite, you're going to get a null. And then as you increase path in either direction, you're increasing the path length from here, decreasing it from here, and you go through maximum and minimum, okay? So this is called an interference pattern, and we often call them fringes. If you see them on a screen, this would be colored, this would have no light, okay? This would be colored, no light, etc. What we're going to see in the slides today is that let me go to another part now. So that's very nice. That's for a point source which has perfect coherence. You might ask, well, why is it falling off here? Why doesn't it just go on at the same amplitude? That had to do with the spectral width of how many waves of coherence there were. It's sort of the diagram is implying that the path length from here to here and from here to here is becoming large enough. The difference in path length is large enough that it's become a number of equal to a number of waves in length, actually how many nanometers, and that length is about equal to what we're going to call a coherence length. It's at that point, this source wasn't temporally oscillating. It didn't have a temporal coherence enough to support those waves, and at a certain point they're not interfering anymore. We'll understand this better later, but this is where we start. Okay, and we're going to find in analyzing the coherence that it's convenient to do it in two parts, what we'll call spatial coherence, and this is the relationship here, and that has to do with how far away or how big is the source. Maybe the source is not a point source. In fact, maybe it's a bunch of point sources and they cover a distance d here, and there's some angle here, and we'll find out there's something here about the spatial coherence. And how many fringes we can see in this direction will depend on how narrow is the bandwidth. It'll depend on lambda squared over delta lambda, which I would understand as lambda over delta lambda, the half out in front. Lambda over delta lambda is the number of coherent cycles or waves multiplied by the other lambda. So you just take one of these lambdas over delta lambda. That's the number of waves of coherence is the phrase I would use. Multiply it by lambda, and there's a factor of a half. It's just a definition. It's no more than how you could define it. Depending on your application, you could leave this out. But for certain reasons, we decided to leave it in. Does anyone want to ask something? So this, you know, is Young's double slit. Oh yeah, why is it, you know, you've probably all heard of Young's double slit. So it's named after Thomas Young in the 1800s, I forget when, but following Newton, basically people thought that and Newton thought, light travels in straight directions, and he didn't completely appreciate the wave nature of light. And Young came along and showed that you could make interference patterns, and he came up with some relationships. But it was Young who showed that there was a wave nature to light. It wasn't just little particles going straight around, or rays of light. It wasn't just rays of light of different, but it was actually had a wave nature to it. So it was Young who gets credit, and all if you look at little histories in optics, he'll be the one who gets credit for correcting Newton with regard to the wave nature of light.
Professor Attwood?
Yeah.
So you were talking about, so the reason we have this fall off as we go to like the further out reflections. So is that, so you said that's because of temporal coherence? Yes, in the source.
Yeah.
We pretty much see that for all sources, that they're not temporally coherent.
That's right. Or they'll have some limited, depends. They could have a lot of temporal coherence or a little. This is sort of exaggerated here to say that this is a point source, but maybe it only oscillated for 10 cycles or something like that. So after only 5 cycles, the degree of coherence was already falling off. By 10, it would be 0. Does that make sense? Or could we discuss it?
Yeah. Okay, so that makes sense. So you're just saying like it, I guess when I think about temporal coherence, I just think about like wave fronts not like coming later from the same source, not exactly matching wave fronts from earlier. But you're just talking about like, oh, if it stops emitting.
I'm saying that you might have 10 cycles, but how do I want to say this? At 10 cycles, if you just went on axis, just looked at the radiation on axis, if you went for 10 cycles of the wave, let's say that you might have a very nice coherence. The oscillation would still look like a very nice sine wave. But maybe after 10 cycles, the sine wave not only starts to drift off in amplitude, but the wavelength starts shifting a little bit. So maybe the first 10 oscillations are really well defined by a single wavelength or frequency. But beyond that, the next few waves start to get a little bit out of phase with each other. So let's see, if we went back to the previous slide, maybe in this diagram here, we would say, well, for this first 10 wavelengths or cycles, these circles would be just perfectly where they're supposed to be. But after that, maybe not quite so perfect. Maybe one's a little bit further than it should be, another one's a little bit less. It starts to get blurry. And so when you were looking at what is the separation between wavefronts, after, let's say, our 10 cycles, it's not so precise. It starts to get blurry, okay? And we would call that the coherence length, the axial coherence length or the temporal coherence length would be, say, something like 10 or 15 or something like that. We'll have measures of it. You know, how much, we'll be precise about that in a moment.
Okay, that makes sense. Thank you.
So we're going to look at this in several ways before we give up or before we move on here. Okay, so here I was saying this is the ideal point source. It's oscillating for all time. It is the perfectly coherent source. And then there are compromises on that where you don't see the full sphere, you only see part of it. It's not oscillating forever, or it has some spectral width or something like that. And so these are just out of definitions, just out of dictionaries. So for instance, here out of Webster's, it says, what is coherence? It's a systematic connection, especially, I can't see it. I do that all the time, don't I? Went the wrong way. Okay, so it's a systematic connection, okay? And or a logically consistent relationship, having having waves in phase and out of phase at a certain wavelength. So this is a more general use of the word, but our use of it fits in perfectly here. Okay, and so that's one measure of coherence, and we're going to look at, oh, and so what is, for instance, this is logically consistent, you know, having a systematic connection. So one of the examples I've used over the years is the phrase foreign policy. Do we have a coherent foreign policy? For instance, if country X decides that they're going to raise tariffs on our cars, we tell them in advance, we're going to raise tariffs on your cars and maybe on your wine too. So, and then when they do it, we have to respond. So that would be a systematic connection between things, all countries having relationships and knowing, if you do this, I'm going to do this, okay? So that would be a coherent foreign policy. An incoherent foreign policy would say, if you raise tariffs on your cars, we're going to do it too, but then they don't do it, okay? Or we change our trading relationships every couple of years. And so people never know quite for sure what is our trade policy, our policy about going to war, etc. So there's another definition here, marked by an orderly or logical relationship of parts that affords comprehension or recognition, coherent speech, okay? And in physics, pertaining to waves with a continuous relationship among the phases. So we were talking about our point source before only existing for maybe 10 or 20 cycles, and after that, it existed, but the phase fronts weren't quite where they were supposed to be. So it was a certain relation among the phases. This is very precise for a while, and then it's not. So I think now we should get to the marching bands. Oh, this is from Born and Wolf. It's a famous book in optics. It was the first book that really had a coherent chapter. That's a bad phrase. Had a chapter on coherence. And I don't know what I should tell you about this. It's a little too much history involved here, but Max Born was a Nobel laureate. Emil Wolf was his postdoc, his young postdoc, just got his PhD. Born already had a book on optics, but he wanted a much more modern book. And he and Wolf were writing it together. He would, you know, outline what he wanted, and it was Emil Wolf's job to carry through. And Born was getting a little upset with Wolf because the book wasn't getting done. And he kept, Emil Wolf told me this himself, Born kept asking me, why aren't you done? Are you still playing with that chapter 10 on coherence? Because they hadn't had a chapter on coherence up to that point. This was 1958. The laser was invented and demonstrated in 1960. So 2 years earlier, this book had come out with a whole chapter on coherence, and it was a big hit. So Born and Wolf, until recently, has been one of the leading books in optics. We were looking before, if you imagine that you're standing next to this pond and you drop a single pebble into the water. What you're going to get is all of these nice spherical waves propagate. They're water waves, but they're going to be these nice waves propagating out. What happens if you drop a lot of pebbles in there? It's going to be a scrambly thing. You're not going to have nice phase relationships. You can do something to limit the differences, but so dropping a lot of one pebble, we would think, well, that produces coherent water waves. A lot of pebbles, not so many. This has personal significance for me because I was once invited to give an overview. It was more than an overview. It was like a half-day school lecture at an optical society meeting on coherence at X-ray wavelengths. And who comes and sits in the front middle seat but Emil Wolf? And at a certain point, I'm giving my lecture about dropping pebbles, and Wolf is shaking his head, no, something's wrong here. So we had to stop the lecture and deal with it. And we came to a common understanding. And then shortly thereafter, he published this paper. He's one of the authors with the ducks, the spatial coherence from ducks. And I was so happy to see this paper because he had been questioning my pebbles, but here he had his ducks. Okay, I showed you this before. This is a common light bulb. It's meant to be, has a hot filament. It's radiating a full spectrum of radiation shown here by just two waves. And it's not spatially coherent. It's just too big here. We'll have a relationship for what we mean by too big in a moment, but it's just radiating out in all directions. The wavefronts are all jumbled and it has some spectrum. And we can do two things to improve that. We could put a pinhole in front of it so that we only sample a very small part, and we could in fact get spherical waves from that. We'd still have some spectral width, shown again by just two colors, and so we could put a monochromator there or a filter to choose only one wavelength. In both cases, when we put a pinhole here, we really knock down how much radiation is coming out. Orders of magnitude of power or photon flux are lost, perhaps in both cases. And if you put the both of them together, you could have a really nice spatially coherent source. And in fact, I have used a light bulb to make off-axis holograms, which I would have thought up to that point required a laser, but we managed. We didn't have a lot of power. This is from the article by Art Charlow, a professor at Stanford, who wrote one of the earliest articles on laser light, he and Charles Towns of Berkeley. And this is from his article. And this is showing that actually you could get all of the coherence that you want in a laser if you basically just put this pinhole inside the cavity. I'll come back to it at the end. But this is the idea of what we call spatial filtering and spectral filtering. And these things, yeah. So now I want to bring up the idea of coherence lengths. So here's our marching band. I think I told you before at Barack Obama's inaugural parade. And they're marching, and if you notice, their left foot is always back. Their right foot is down, left foot is not. So they're all marching coherently in the sense that they're all putting their certain foot down at the right time. And how do they know how to do that? There's a man here, and he would be the one who's calling cadence. So he would make some sound every few seconds that they recognize that's the command to put your right foot down, okay? And so we would call this a coherent marching, okay? But how could this get, under what circumstances might this not work quite so perfectly? One is if they're surrounded by a noisy crowd, so they can hear this guy if they're close. So maybe these people near him can hear him well, but the others, it depends on the noise of the crowd. Sometimes they hear him, sometimes they don't. They get that foot back down when they're supposed to, or they don't. It could be windy, so his voice is blowing in one direction. The people in front of him don't hear him so well. So all of these things could affect how well these different people are putting their foot down at the right time. And we could make some measure of that and say, well, up to a certain distance, they're all doing pretty good at putting their foot down. But beyond that, it gets a little fuzzy, and further away, they're just completely random. They don't hear anything. That distance we would call a coherence length, okay? Maybe how many people coherence length or something like that. And it could have a directionality to it because of the wind. And we're going to have a directionality in the sense that we're going to look at waves propagating in the forward direction, and the phase properties orthogonal to that, the wavefronts. Okay, so we're going to have two measures. One is temporal coherence, and one is spatial coherence. One has to do with how well the radiation appears to come from a point source. I mean, if it came from a point source, we'd have spherical wavefronts. Maybe the wavefronts not quite so spherical in some sense. Maybe they're a little wobbly, or who knows what. But they don't appear to come from a point source. So that we're going to call that some measure of that spatial coherence. Temporal coherence in the propagation direction. And so here is shown some radiation which has some spectral bandwidth to it. It has a wavelength lambda, but there's a little uncertainty in that wavelength. And so this is a wave the solid line is showing goes so many cycles, the solid line, but the dashed line, also from the same source, and maybe there's a continuum there between over this spread of wavelengths, but the dashed line is showing somewhat longer wavelength coming from the same source. So the dashed line, because the wavelength is longer, at a certain point, it's getting out of phase. If you add up the electric fields at a short distance, they add up pretty well. But if you go a certain distance too far away, you might get a 180-degree phase shift. Now, if you add them up, you're at the null in the diagram. They're completely out of phase now. There may be no phase relationship left, that this is some random spread of delta lambda. There's just no phase relationship left. So there's only a coherence length up to some distance. So we're just defining, I define here, a coherence length arbitrarily as being the distance where this spectral width has led to a phase difference of 180 degrees. So some spectral width is leading to dephasing. And we're going to call, this introduces the concept of temporal coherence. So we were looking before at our spherical waves propagating out, and we said, well, for about 10 cycles or 10 waves in this spherical pattern going out, things are pretty well placed. The phase fronts were really close to just a wavelength apart, but as we went further, because of some uncertainty in the source, particularly the spectral width, the phase fronts were no longer quite where they were supposed to be. They're getting out of phase, and at a certain point they become random. And so that's our coherence length in the propagation direction, which we'll call, and it depends on the spectral bandwidth. Okay. Spatial coherence would be when we look back, when the interference pattern we record suggests that we didn't get radiation from a point source, for instance. We never did get a full amplitude here. There was something indicating that it wasn't really a point source. Okay, so for instance, it could have been a few point sources. Maybe they were all close together so that the resultant added wavefront was pretty close to what it was supposed to be, but it had a little spread to it. Okay, maybe even some wiggles onto it. So when you sample it in two places with this aperture here, when you sample the two places, maybe sometimes for some part of it, you're getting on axis, everything's okay, but slightly off axis, the differences in wavefronts, because this thing is reaching with a slightly different wavefront than phase rather than this one, you start to get some jumbling on this. And that will reveal something about the spatial nature of the source. We're going to call that spatial coherence. And yeah, so I would recommend, I want to stop just after this slide, maybe I'll stop and we'll talk about it. So here's our point source oscillator again, radiating spherical waves, not shown completely, but they're all there. And if we knew the phase at one point, P1, we could tell you what the phase is going to be at some other point. We just have to go out a certain number of waves, and anywhere along that contour, we would know what the phase is. It's at a peak when this one's at a peak. It's at a minimum when this one's at a minimum, something like that. Okay, and so that would be the nature of a point source. And we in general break these properties down of the phase relationships this way in the propagation direction and the phase relation transversely. We break those down, and this in the transverse direction, we call it transverse or spatial coherence. And in the propagation direction, we call it either longitudinal coherence or temporal coherence. We use the phrases equally. So I hope this is starting to get the ideas in about what we mean by spatial and temporal coherence. We're going to find in a moment that if we ask about what is the coherence length, where do things become dephased, we're going to find that there's a temporal coherence length given by this formula, lambda squared over 2 delta lambda, which we saw a moment ago, and which generally, for myself, I think of it as I take one of these lambdas and divide by delta lambda, and I that's kind of a spectral purity, and multiply it by the remaining lambda. Okay, that's a coherence length. So it depends on the spectrum. And in this transverse direction, it's a little less obvious. In fact, it's a lot less obvious, but there's going to be a relationship between the size of the object, if it's not a point source, how big is it, and how much of an angle do we collect, finite angle that we collect. And we'll say that a source is transversely coherent if its source size and divergence are roughly equal to lambda. There'll be different measures. These are RMS uncertainties here. We'll see later. Maybe we'll write it in terms of full width at half max. For completeness, when one normally talks about theory of coherence, this is what people would do. They'll say that there's a coherence factor. This is normally what they would show, which is saying, what is the expectation if I knew the field at some point, P1, if I knew the electric field at E1 at some time, what is the expectation that I would know it at some other point, P2? And so coherence becomes a theory of expectations. Okay, if I knew it here, would I know it there? It would depend on what was the degree of coherence in this source and how far these two were apart and how much of it was longitudinal and how much is transverse. And these are just normalization factors. So this has a maximum of 1 and a minimum of 0. So full coherence would be when you could totally predict P2 from P1. This mutual coherence or normalized degree of coherence would be 1. If you know P1 and you have no idea what P2 is, that would be incoherence. So I think, yeah. So now we're going to try and derive these two relationships, but maybe please be brave and make comments or ask questions, because in general, this is, it may see, it's more challenging actually than other topics. It's requires some getting used to. So I think I'm going to try to give you some examples today that demonstrate these things, but also give you some applications of where you might see it. But does anyone want to offer some comment? Yeah, please.
So E here, is that electric field?
Yes, E would be electric field. It could have been magnetic field. If it was a water wave, it could be the height of the wave, or it could be a sound wave, it could be pressure, you know. So it depends on the kind of wave. But for us, electromagnetic waves, X-rays, we could take electric fields, right?
So it doesn't have to be in a vacuum, correct, to apply this formula?
Exactly. This could be anything. So this could be propagating in some medium. And yeah, and it is good to think of it too as water waves. You know, you have some waves which are on the surface of the water outside off the beach, and they're propagating along, and you see the waves, and you know they last for a certain number of cycles, and then they dribble away, and another wave comes along, and it's what is the expectation if you look at the peak of a wave that you'll know the peak, you'll know what the phase of the wave would be a little bit, you know, a few cycles away or something like that. Yeah. So this coherence theory, it goes far beyond optics. In fact, in most optics courses, they say little or nothing about coherence. It's left as a separate topic. So something else?
How can you, I guess, ensure that the longitudinal coherence length is longer than, is it just with a higher wavelength or smaller, I mean, smaller difference in wavelength, that this bottom?
Yes. No, good question. So one of the things we'll do is, or one thing we do is we perform an interference experiment. Somehow or other, we take our wavefront and we split it into two parts and bring it back together again at some angle, let's say. And if we did it right, we should see this beautiful interference pattern, fringe pattern. And if the fringe pattern doesn't go as far as we thought it was, it's because the source wasn't as coherent as we thought. And that could be so we could see a fringe pattern, let's say my fingers, something like that. It could be that the fringe pattern extends rather long. We can have some measure of it. How far does the fringe pattern extend in this direction? And we still get nice interference patterns. And how much laterally? And so for instance, remember putting the pinhole in front of the light bulb. You could start with, in fact, let me go back to it. Yeah, I said, oh, you put this little pinhole here and you could get nice spherical wavefronts. Well, suppose you put the pinhole here, but you didn't make it small enough. Then you wouldn't get these nice spherical waves. You get something that was sort of looks spherical, but not so perfect. And you'd close down this pinhole until they really looked spherical. Okay, and in fact, when you split the wave and put it back together again, you got really nice interference patterns. So what we're going to come up with in just a moment is an estimate of how big should the pinhole be for the wavelength of radiation we're using in order to get a nice pattern. And we're going to come up with this. It's not quite cheating, but it's sort of cheating on life to use such a simple method to come up with a formula for what not such an obvious situation. So I'll show you, I'm going to try and show you some examples where you, first of all, we're going to derive the formulas and then we'll apply them. So we'll start with this one about a radiation source. This is propagating in a certain direction. So you can imagine that on the transverse plane, they're nice spherical wavefronts. And we're just worried about the effect of the spectral bandwidth in the propagation direction. And we're saying that by our little diagram here, after going some number of cycles, it becomes dephased. There's no longer has a predictable relationship and a nice interference pattern and some spectral bandwidth. So what is this coherence length in the propagation direction? Well, let's just say that this is n cycles. The dark line is n cycles, and the dashed line is a half cycle less because it was a little bit longer, and it's a half cycle out of phase. So this is equal, this length, this coherence length, which we're arbitrarily saying is when the radiation becomes a half wave out of phase, okay? So we're going to say that this coherence length is n, the number of cycles here, times the wavelength, just geometry, okay? But we could also say that for the longer wavelength, the dashed line, the wavelength now is lambda plus delta lambda, and it didn't go n waves, it only went n minus a half. So this same coherence length would be n minus a half multiplied by the wavelength, which is now lambda plus delta lambda. And if you multiply this out and equate the two, lambda coherence equals lambda coherence, so this equals this, you'll get a solution for n, that n is equal, so you're just solving two simultaneous equations. When you solve them, you'll find that n is equal to lambda over 2 delta lambda, okay? So that the coherence length is this n multiplied by this lambda. So it's this is it. So this is a kind of simple way to get a measure of a longitudinal coherence length. And basically, everybody in the world would take this formula and say, that's it, that's it. Actually, the only question might be this factor of 2. That was pretty arbitrary how you said, oh, we're going to be out of phase here. Exactly a half wavelength. You know, maybe for our experiments, we can actually afford to be only a quarter of a wave, or we could afford to be more. This factor of 2 was arbitrary. Also, the shape, was this a Gaussian shape or was this a square shape? All of these things go into what's this numerical constant? But I would say for our level of interest, we're happy with this, okay? And my dear friend Emma Wolf said that although he didn't use that in his book, he found the factor of 2 just fine. Okay, so this gives us a measure for a coherence length in the propagation direction, which depends on spectral bandwidth. So we're going to use this. This is going to be one of our relationships, and we need one for spatial coherence. And so this is, it says, a practical interpretation of this. So if this is a point source, it's going to produce spherical waves. So we're going to associate spatial coherence with a spherical wave. So, well, why did you say a spherical wavefront? You could have said a cylindrical wavefront. Well, in practice, in the real world, we don't see cylindrical waves nearly as many as we see closer to spherical waves, more three-dimensional. And so we're going to associate a spherical wavefront with a point source. Seems reasonable. Now we have to ask a question, well, how small is the point source? You know, are we talking about X-rays, or are we talking about visible light, or are we talking about microwaves? You know, for X-rays, a point source is probably going to be pretty small, some measure towards the wavelength. For microwaves, what is a point source to generate spherical waves? It's probably microns or something like that. So here's where we take our cute little trick. We're going to use Heisenberg's uncertainty principle. Okay, which these are vector quantities. Delta uncertainty in position and uncertainty in momentum is greater or equal to h bar over 2, where these uncertainties, excuse me, are RMS quantities. They're RMS meaning 1 over square root of E. So if you plotted, let's say, spectrum with some width to it, it would have a half width. These are in Heisenberg uncertainty principle terms. These are one-sided measures, and they're where the peak drops off to 1 over square root of E. So if you looked up Heisenberg's uncertainty principle, this is what you'd find, and they may or may not tell you that these are RMS quantities. So by Heisenberg's uncertainty principle, the smallest source size you can resolve, the smallest d you can resolve, depends on the wavelength and the angle, and we're going to see that now. So how did I get this relationship, which I'm looking at from here? I'm going to make a little diagram, hopefully I'm praying it's in the next slide. It's not. Well, maybe I should have shown you that for a second. So here's our Heisenberg uncertainty principle. Standard deviations of Gaussian distributed functions. This is an example of, it's an undergraduate physics book, but it's a really good and popular one. We used it here in Berkeley for many, many years. So here's the relationship. But for photons, the momentum is h bar k. So I'm going to replace p, the momentum, by h bar k, and it becomes an uncertainty in k. Okay. And so this is our relationship. We can get rid of the h bars on both sides, and k is 2 pi over lambda. Oh, I'm sorry. What is the uncertainty in k? So here's our source. It has some width, which we're calling a diameter of 2 delta x. Okay. This is delta x is an uncertainty in position. So this is an uncertainty in the size. And this radiation is going out, and we're observing it within some aperture. So we're only looking at a half angle of theta. And k is the vector, is the wavefront, k is the wave vector, 2 pi over lambda, but it has a directionality to it. If our radiation is almost monochromatic, quasi-monochromatic, then the uncertainty in k is not so much uncertainty in wavelength, but it's uncertainty in direction. So the uncertainty in our radiation here, this is for a quasi-monochromatic. It could be 1 part in 100, that would be fine. But at any rate, so delta k, the uncertainty k, has to do with this angle. And we would call it as k delta theta. So the uncertainty in k is whatever k is times the uncertainty in the angle. So this delta k became k delta theta. And And we're going to take, I'm putting this factor of 2 over here because I want to have a size that's 2 delta x. So I'm taking this 2 and put it here, and it's k delta theta, but this is 2 pi over lambda. So I'm taking the 2 pi, I'm going to take this as just a scalar in a moment. In fact, here was the diagram for that I should have used for what is delta k. So here's k going, radiation is going out with some wave vector. That diagram is, this is k, this is the angle. When you see a photon coming out, you don't know where it came from. It could have been anywhere in this region. That's the uncertainty. So this is a little trig to relate delta k is equal to k delta theta for small angles. Okay, and if I take the scalar parts of it and I replace this by 2 pi over lambda, I get that the uncertainty in position multiplied by the uncertainty in angle, this is the uncertainty in angle, is lambda over 2 pi. So we would call this, we would replace the delta theta, the uncertainty in theta by theta. So we'd have d times theta equals lambda over 2 pi. So according to Heisenberg's uncertainty principle, the smallest, for us to judge that a source size is about equal to d in the limit, we would say it depends on wavelength, the wavelength and theta. So this is telling us if our wavelength is an X-ray wavelength, this is going to be d. We'll have to say over what angle did we collect the radiation? How big a view did we have of this point source? Could we look to the left or look to the right? Again, these would be uncertainties. So this is giving us a relationship because of the nature of which Heisenberg wrote the principle. These are RMS quantities. This is RMS uncertainty in position, actually twice because of diameter. And this is RMS uncertainty set by the aperture with which we view it. So radiation which meets the limit, it's almost like a point source, will satisfy this relationship, d dot theta equals lambda over 2 pi. So if I told you that we had a wavelength of, let's say, 10 nanometers, and we collected radiation over some small solid angle, maybe this is what would we say is a milliradian. We collected radiation at a milliradian, so that's 10 to the minus 3. We would say the smallest diameter we could prescribe with any detail would be lambda, the 10 nanometers, over this factor of divided by 10 to the minus 3. So it would be 10 nanometers times 1,000. It's going to be 10 microns. So what's that saying is we couldn't tell if it was, if we looked at that 10 nanometer wavelength and we collected it over a half angle of a milliradian, we couldn't tell if it was 10 microns or 5 microns. We could not tell, we would not have the resolution to see it. Optical resolution looking backwards, we couldn't tell the difference. So that's what we mean by the uncertainty in the size. So we're using this point source analogy, and we're coming up with a formula that says within some viewing angle, we can tell you, this is, for instance, going back to that light source from Art Charlot's article, how big a pinhole should we put there? Well, let's say that we were looking at green light, which is 500 nanometers divided by, let's say 600 nanometers, slightly, maybe it's yellow light. 600 nanometers divided by 6, so this would be 100 nanometers. And depending on the angle we viewed it with, it would tell us how big a diameter. So if this was, what did I say, 100 nanometers, and we looked at it with some, let's say pi over 4, a big angle, we would divide this by pi over 4. It'd be 100 nanometers divided by pi over 4 is almost 1. So it would tell us that the pinhole that we put in front of that would have to be about 100 nanometers for visible light viewed with a large angle, okay? So that would tell us how big a pinhole to put. And so let me tell you that at the ALS and several beamlines, or one beamline in particular, we simply use this formula to predict how big a pinhole we make. Then we look at the interference pattern to see, did we get the interference we thought we were going to get, very high modulation or not? It turns out that these are RMS quantities, which accelerated people like and coherence people like, but laser people and myself prefer to write them not in terms of RMS quantities, but full width at half maximum. So if this was a diameter of full width at half max, and this was, let's say, 2 theta, but not RMS, 2 theta full width at half max, you just, the Gaussian distribution, this relationship would become d times 2 theta is roughly lambda over 2. It's easy to remember. So this becomes our spatially coherent limiting factor. If our source meets this criteria, it's going to generate waves that, as far as we can tell, are spatially coherent. If we made it any smaller, it wouldn't make a difference to our interference pattern. If it were bigger than this relationship, we would say, oh, it's twice diffraction limited. Then we would not get these nice spherical wavefronts. We'd get some variation here.
Professor.
Yeah.
Can I just confirm, you were talking about like the error in K comes from this delta theta. Does that mean that there is like no delta lambda, like all of our wavelengths are exactly the same? And
you're correct. You're correct. I said it, but maybe I didn't give it enough emphasis. This is assuming that delta lambda over lambda is small.
Okay.
So in the previous one, in this one, we could have said, okay, well, suppose lambda over delta lambda is even 1,000. That's a reasonable number in an experiment, okay? If that was 1,000, we get some coherence, longitudinal coherence, but then we go over here. This relationship is for quasi-monochromatic. So lambda over delta lambda of 100 would be good. So if that's the case, the uncertainty in the wave vector is not so much by the magnitude of K, but it's the uncertainty of which way it's pointing. So this is a vector uncertainty. It could have a variation in amplitude, but we're saying, no, that's not so much because the spread in wavelength isn't so much. It's really an uncertainty in angle.
Okay. So when you were saying, oh, we can't tell whether the wavelength is 5 nanometers or 10 nanometers, it's monochromatic. We just can't tell if our pinhole is too big. We then.
That's if we make our pinhole a little bit bigger, we'll start to see that the fringe patterns don't look so good. I'll show you an example in a moment with X-rays.
Okay.
But if we made it smaller, it wouldn't improve anything. If we took half the diameter, we'd actually cut the flux by 4, and the fringe pattern probably would be marginally different.
Got it.
So these are really good discussion points.
Practically, for determining the angle theta, the half angle theta, would you put a detector at the distance that you care about and then watch for the first interference fringe, like the first dark fringe? Is that what's going on?
Yeah, so something like that. The angle would be set by your experiment. For instance, if you need coherent illumination of some object, it would be how big is your object and what's the distance from the source. That would set the angle. So this could be a pretty small angle. It could be, okay, I want to coherently illuminate a grating which has 50 lines. Well, okay, put my grating here, 50 lines times whatever the spacing is. That would give me a size. And how far is it from the source? Maybe several meters, 10 meters from the bending magnet or undulator at the ALS or high harmonics experiment. So yeah, so the aperture is being set, for instance, by your sample size or your detector size or something like that, and how far away it is. This is just a slide to say that if you looked at the propagation of a Gaussian wave, which is what you'd get out of a laser, a good laser, which has a pinhole actually inside the cavity, it would produce a Gaussian wave. and it would propagate, it would increase radially as a function of z, some angle. And if you analyze that Gaussian wave propagation, you'd find that you get this exact same relationship shown at the lower right-hand corner. So I don't want to take time to talk about that, but for instance, this is, you could find this in Siegmund's book on lasers. And in fact, one time Tony Siegmund and I spoke back to back. He was talking about visible lasers and I was talking about undulators at the ALS and spatial coherence. And we both showed the same formula, which we both found amusing at the end. Yeah, so here's a Gaussian wave. So this is some properties of a Gaussian wave, which become useful to us later. Just remember that you have it. And it's also, these formulas are in that file I gave you of formulas that you may want to use. And then basically, here's a 1 over square root of E. This would be the RMS radius, spatial radius. The full width at half max is bigger than the Gaussian one by this factor, 2.35. It's just a matter of doing some geometry, okay? And a 1 over E squared measure is actually twice the RMS. So laser people often use full width at half max, or sometimes they'll use 1 over E squared. They'll say there's, for instance, I forget what the number is, but something like 90% of the energy of a focused laser beam is within a 1 over E squared radius. That is a distance of a radial distance of a spot size where it drops to 1 over E squared. So these are some formulas. And there's also formulas for depth of focus or depth of field. You focus the radiation down, it'll expand in a distance called the Rayleigh range, okay? That's shown here. And the depth of focus is actually two Rayleigh ranges, one to each side. That would be the depth of focus. So you'd say you're in focus here, but within a Rayleigh range is not much of a difference, or within depth of focus, not much of a difference. And so for those of you who are familiar from some optics, the depth of focus is typically plus or minus a half, meaning this side or that side, that's the plus or minus, lambda over numerical aperture squared. So we'll use these formulas later and we'll talk about them when it's necessary. So we're running out of time. Here's an undulator beamline. Here's a picture, a representation of an undulator. It has some period, magnetic, so it's for those of you who don't know, an undulator is a set of periodic magnets where this would be north and south, but the next one is reversed, south and north, north and south. So there's a periodic magnetic field over some number of periods, and radiation comes through it, and we can get a lot of power out of one of these. We can, at the ALS, you could typically get a watt of power in a bandwidth of 1 over n. So if there's 100 periods, it would be a 1% bandwidth, we could get a watt of radiation. But it's like the light bulb, it's a little too big. The size of the source size and the divergence angle within that contains the bandwidth we're interested in, bigger than the formula we had before. So we'll put a pinhole in front of it, just like we did with the light bulb before, and we'll have some angular aperture, which could be set by our sample or our detector, and what's the distance back to the source, or back to the pinhole. And this product of D and theta has to satisfy that relationship if we want to get spherical wavefronts. So this is an image obtained at 600 EV, 2.48 nanometers, obtained with a 2.5 micron pinhole here, which came from that formula, the D dot 2 theta equals lambda over 2, the full width at half max. That indicated a 2.5 micron pinhole. This was a PhD thesis of Chris Rosefjord, and Yanwei Liu had just gotten his PhD, so he was there also. And you saw him in some of the pictures. He was one of the people who's now at SLAC, and Chris is in Washington, DC. She taught at MIT, and then she taught at Maryland. But anyway, so this was ALS, excuse me, beamline 12.02. And this is a so-called Airy pattern, A-I-R-Y, after George Airy. And basically, this is the central lobe, which is oversaturated. Basically, if you were looking, you probably only see this and then a dark ring, and then you'd see a little bit of light. But here, we've saturated the middle part to see all these other rings. So these are representing the interference pattern. Basically, it's telling us that the X-rays coming out of this undulator and going through this pinhole, seen within this angular aspect, we can see a lot of fringes here where these are just about close to perfect circles. And so we would think that, oh, this would provide a really nice fringe pattern. How could we measure maybe we can get one of those Young's double slits, and rather than just look at the pattern here, maybe we could put 2 slits or 2 pinholes. So we call it Young's double slit, but actually I went back and read the papers of Thomas Young, and he used pinholes also. It's just a matter of how much flux he needed. So 2 pinholes were preferred. If there wasn't enough light, he'd use 2 slits. So the next, oh yeah, so this is just what a beamline at the ALS might look like. So here's our undulator, periodic magnet structure. It says that the period is 8 centimeters and the number of cycles, I forget, is 55 in this one, okay? And so there's a lot of radiation comes out, a lot of power, and there are water-cooled apertures to only allow the radiation we really need within our bandwidth. There's a plane mirror that's inserted that directs the radiation into our bandwidth. This is the electrons get turned by a magnet, so they don't come in. And then there are some optics, and there's a grating. There's a grating and an exit slit. So that's our monochromator to choose the bandwidth. And this is the radiation going through the beamline, and we have different applications of it. One of the things we would put here is a pinhole someplace, and then we would measure what's going on. So this is saying that a little bit more. I think I'll come back to this later because it's not so essential. It's just basically saying when you put the pinhole for spatial filtering and you put the monochromator in, you lose a lot of power, but we're not surprised at that. This is just a reproduction of that same photo. And this is just a reminder now. Okay, we think we have a nice point source, just one, and we're going to put Young's double slit, double pinholes actually, and we're going to look at the interference pattern and see how good does it look. And in fact, what happens if we spread the pinholes a little bit? Okay, so here's, this isn't the exact same pattern that I showed you before. This I think is from Chang, and this is at an EUV wavelength. Ah, it is. It's at 13 nanometers. And in this case, is the undulator and the pinhole was here, and there's a grating with an exit slit so that we're doing spatial filtering, spectral filtering, and then rather than put the screen and just record those nice rings, there are 2 pinholes placed here. And and for instance, when they're placed here, you see that you get this really nice interference pattern from them. So it's saying that the pinhole diameter that was chosen was pretty close to perfect. If it had been perfect, these nulls would have gone down to 0. That would be pretty much the only difference. So this is showing that, okay, the pinhole was a little bit too big, okay? Another question is, we were interested in coherence lengths in the direction of propagation, but also laterally. How far along these fringe patterns laterally can we go and still get good coherence? So one way to do that is with our Young's double pinhole. And here is what happens. When you have the 2 pinholes 3 microns apart, you get this beautiful fringe pattern with very high modulation. So the coherence length is clearly bigger than that. When you go to 4 microns, still looks really good, but you notice the bottom part is coming up a little bit. Okay, that was at 4 microns. If you go to 6 microns separation, what does that mean? That means you're moving these pinholes apart now to 6 microns. Now the modulation is pretty good, but maybe this is a break point, because if we go any further, like 9 micron separation, the interference is becoming quite faint. So we might say here that the lateral coherence length is something like 6 microns. In other words, if we put the pin, if we sample our radiation in this plane by just 6 microns, that's about the lateral coherence length. Okay. Okay. So these are applications now. So we're 10 minutes away. I think probably we should stop now. This is going to be some applications of this spatially coherent radiation. Yes, making holograms, X-ray holograms have been made, and some other things that I want to tell you about briefly. This is about how a scanning transmission X-ray microscope works, but I'll leave that for next time. I think there's enough concepts here for you to swallow. I'd urge you to have a look at the chapter. Don't get lost in any mathematical details. Just see if you get the concepts right. A lot of the diagrams are either from the book or quite similar. And maybe it's a good time if anyone has a comment.
Professor?
Yeah.
I'm a little confused on that last slide you showed us.
Oh.
Why we would expect the nulls to go to 0 if the pinhole is perfect.
Well, if the pinhole was perfect, then we would have pure spherical waves, and the interference pattern would look like this. It would really go to 0. The path lengths would have changed so that the two waves from here, this one coming this way, and this one, if these are perfectly spherical wave fronts, whoa, which way do I go? If this is a perfectly spherical wavefront, same amplitude, and it's just a phase difference here, then when they interfere destructively, we should get a real null. The only reason we're not getting a real null is because these wavefronts here weren't quite so perfect, at least at the distances we measured them. So it's how well this goes to a null is telling us something about the ability of the radiation from this area and this area to interfere. In this case, to interfere destructively. So we can't tell at the top part. And here we're saying, well, they interfered constructively, and we got a maximum. But in this diagram, I didn't tell you what maximum should be. We just normalized it to 1. Maybe it should have been, if it had been a perfectly spherical wavefront, probably this would have been higher and this would have been lower. But because it wasn't a perfect wavefront, we didn't do either one. We just modified a little bit.
Got it. So no matter how good of a job we do deciding how to space our pinholes, if our wavefront isn't perfectly spherical, we're never going to get those nulls to 0.
Yeah, exactly.
Okay.
That's perfect. And so this would be, so this case was for an undulator at the ALS, but for any source that you look at, you'll have these same kinds of issues. So for instance, when would it not matter? Several of you are working on PhD theses which involve CT scans, or where you're basically looking at some object, but you're just making a shadow of it, and then you're rotating the object through 180 degrees, for instance, okay? But you're just making a shadow. When you're just making a shadow like that, these coherence issues simply do not come up, okay? So that would be a case where we don't care. But if we want to make a hologram which involves interference, it does matter. Or if we want to do interferometry, which is a common laboratory tool for measuring phase shifts or how thick thin films are, all kinds of things like that, we form interference patterns which are accurate to a fraction of a wave. Yeah. And so we want to do that in the X-ray region also. Okay, any other comments, or we're pretty much ready to break? So Defon is probably listening, but I have 4 problems for you for chapter 3. And I want to, Defon and I normally go over these first, and it's always good to proofread them and make sure you're not putting some arbitrariness into the question. So we'll go over the 4, but they're mostly going to be on the use of the website. And we'll give you the website, remind you of what the website is. And yeah, probably there'll be some advisory notes in the homework about issues you may come up against when you're looking at this. For instance, when you look at the website, it'll ask you, depending on the question, it'll ask you, do you want a curve or a table? You just have to look and just let them just say what you want, how you want it to print out. So if we're asking you, what's the reflectivity, perpendicular, normal incidence reflectivity at a certain, for some material and a certain wavelength, I found it convenient because the way the website asks you, it asks you over some range. So if we wanted the answer over 80 EV, I would make it like, say, 75 to 85 in sort of so many EV steps, and then ask it to just give me a table. And that, I found that to work quite convenient. In other cases, you want curves, you're asked to give curves for delta and beta, the website will just do it for you. So you should be able to get everything you want. And if you don't, send an email to one of us asking, just saying what the issue is, and we'll see if we can help you fix it. Okay, have a good weekend, and